half-life. Half-life. Now I'm going to define half-life with respect to our rate of reaction here. Is that okay? And half-life is simply the time it will take for the initial concentration of the reactant to reduce to half, to become halved. Or you can define it in terms of final concentration as the time taken for the final concentration to become half of the initial concentration. And of course, you know that half is 50%. Now, on the board, we have the definition here. Is that okay? Now, what are the parameters, the value of the final concentration, the value of time at half-life? That becomes something of interest for us to determine. Is that okay? So at half-life, it's important for you to know that the final concentration, Ca1, will become 50% of the initial concentration. And 50% is 50 over 100, which is the same as 1 over 2. Is that not so? So it's going to be 1 over 2 of initial concentration. And then time, we're going to replace it with T half. Which means if we go back to equation 4a star, that equation that we derived previously, it's used to calculate the final concentration at any given time for zero order rate of reaction. Remember, that is what we are treating, zero order. So we're going to replace T with T half. And if we substitute it into equation 4a star, it means that the final concentration Ca1 will now become 1 over 2 of the initial concentration. And that will be equal to the initial concentration minus Kt, where this T will now become T half. If we work on this equation, pick this CaO to the left hand side, we'll have this equal to negative Kt half. Half CaO minus 1 CaO. Half minus 1 will give you minus half. Is that okay? So that's going to give us minus half of initial concentration equal to minus Kt half, where the negatives will cancel out, and then if we make this half-life subject to the formula, it will be to bring this K as a denominator here. So it's going to multiply this denominator 2. Therefore, the half-life for a zero order rate of reaction is equal to the initial concentration divided by what? 2 times the rate constant. You know, we've been used to the first order rate of reaction half-life, which is T half equal to 0.693 over the constant there. Of course, you've seen another that for zero order, you still have its own half-life, which is different from that of first order. And of course, it might interest you also that second order's half-life is different from these two, right? Okay, now what's the unit of the rate constant K for zero order rate of reaction? Judging from equation 3, which we have initially, that is the differential rate law for zero order, you notice that it is dCA over dt. Ca is concentration moles per dm cube or moles per liter, and then time in seconds. So if you put that, the concentration term and the time term in terms of the unit of the rate constant will now become moles per liter per second, or moles per dm cube per second. Does that make sense? Take note of this conversion factor. 1 dm cube is the same as 1 liter. In the next video, we're going to introduce first order rate of reaction, where we'll also derive the equation for calculating its final concentration and, of course, the half-life. So in this video, let us now look at the half-life for a first order rate of reaction. Previously, we established the half-life of zero order rate of reaction, where T half is equal to the initial concentration CaO divided by what? 2 times the rate constant for zero order rate of reaction. So for first order, what do we do? Now we already have derived this equation, so I want to recall this. In the previous video, that was equation 4a star, right? So at half-life, what's going to happen? At half-life, let's see the condition. At half-life, we know that the final concentration Ca1 will be equal to 1 over 2 CaO. And then the time will now become T half. Is that okay? So we are going to substitute these into this equation. So it implies that in place of Ca1 final concentration, you're going to put 1 over 2 CaO and then minus CaO equal to minus Kt half. Now this is ln of this concentration term, ln of this concentration term. We know that ln is the same as logarithm to this e, so it shares the same law for logarithm. Is that okay? So it shares the same law, and so we're going to apply that here. we have that ln of this term minus ln of this term. When you're subtracting log to the same base, you're going to pick one of them. So I'll pick one of the lns. And I'll have 1 over 2 CaO. You divide this term by this term. So I'll divide by this concentration term and then minus Kt half. Notice that these initial concentration terms will cancel out, and once that happens, I'll have ln half to be equal to minus Kt half. If you press your calculator, ln of half would give us minus 0.693. And that will be equal to minus Kt half, alright? So the negative terms will cancel out. And once it cancels out, we can make the half-life T half subject of the formula. Let's do that. So our T half is now going to be equal to, it's going to be this term, 0.693, right? Divided by K. You agree with us, isn't it? So that will be 0.693 divided by K, where K is the rate constant for first order rate of reaction. Now, this equation is a very common equation in the study of chemistry, in the study of physics, whenever you are dealing with a decay process or any equation that is modeled in line with first order rate of reaction. Is that okay? So take note of that. This is how to calculate the half-life for a given first order rate of reaction. Please note, unit of K for first order rate of reaction, for first order rates of reaction. Okay, from the equation K equal to negative dCA all over Ca dt. Say our equation 3, if you make K subject of formula here, that's the equation 3 we had in the previous video. If you make K subject of formula, you're going to get this term. Is that okay? Now, if you look at this, one could say, okay, fine, even if this is a differential coefficient, but the concentration terms can go off, and if that happens, this is going to give us 1 over T. Let's forget about the differential coefficient term now. And so, do you see that the unit of K will now be what? Per seconds. So take note of this. This is the unit of K for first order rate of reaction. Remember, for zero order rate of reaction, it is moles per liter per second. But for first order, it is what? Simply per seconds. In this video, we want to find out the time during which the final concentration for a second order reaction will become half of the initial concentration. So we want to derive the half-life for second order rate of reaction. Now on the board, we already have derived this equation for calculating the final concentration for a given second order reaction. Is that okay? So we're going to walk through from here. You know that at half-life, these are the conditions. The final concentration will become half of the initial concentration, and then time will become what? The half-life time, that is T half. So coming to this equation, if we move this 1 over initial concentration to the left-hand side, we are going to get this equation. Is that okay? So let us now substitute the condition at half-life. So it implies that this will give us 1 over, in place of this final concentration, we're going to put 1 over 2 times CaO, and then minus 1 over the initial concentration CaO equal to Kt half. Now, having written this, mathematically, these 2 will go up. Is that okay? These 2 would go up here to become 2 all over CaO minus 1 over CaO equal to K times the half-life. And these terms, since they have common denominator, if you walk through it using LCM, which is CaO, they have common denominator, so you can just subtract the numerator. 2 minus 1 will give us 1. Pick one of the common denominators. So we're going to have that this is 1 over CaO equal to Kt half, alright? So with this, we can now make the half-life subject of the formula. If I make half-life subject of formula, I'll have T half to be equal to 1 over this rate constant. We multiply the initial concentration, and of course, this becomes the half-life equation. I'm going to call this equation 5 because you would recall from our previous video that we already established this as equation 4a star. Now that we've gotten the half-life value, alright, I now want to tell you that the unit of K for second order for second order reaction. For second order reaction is, so this the unit is going to be liters per mole per second, or you can write dm cube per mole per second. In fact, after looking through the unit of zero order, first order, and now second order, it was discovered that dimensionally we can say that the unit of K can be obtained from this. We know that K is equal to concentration raised to power 1 minus N divided by T, where N equals order of the reaction, So if we have this equation, we can actually get the unit of rate constant for any order of reaction. All you need to do is to substitute the units of concentration, which is either moles per dm cube or moles per liter. Then this is what? Second. Remember, N is order of the reaction. So you can walk through that for zero order, where N will be 0, for first order, where N will be 1, for second order, where N will be 2. And of course, you get the unit of K easily without stressing yourself memorizing it for each of them. This equation can help you.